So we're going to continue working on the preventive maintenance case study. In a previous tutorial, we completed the data preparation. In this tutorial, we will start modeling. We will be trying 4 different models, 2 models from core statistical background like logistic regression and linear discriminant analysis, and 2 models which are relatively modern models, machine learning models like decision trees and random forests. We will in the process show you a fair comparison between these models, and we will also be covering hyperparameter tuning. Finally, since the data that we are working on is an imbalance data, which is how most of the natural data sets are, we'll also be talking about the importance of class imbalance treatment. So this in itself is a complete tutorial. Now, just in case you're not familiar with any of the data pre-processing techniques, or you're not familiar with any of these models, then you may refer to our tutorials on these topics. The best part is that all our tutorials are very visual in nature, where in a step-by-step way, we've broken down most complex topics in data science and machine learning in the simplest possible way. So if you are a serious learner of machine learning or data science, then you may consider subscribing to our channel and make sure that some of our playlists are saved to your favorites because you'll be needing them. With that said, let's get started. Now, the next piece of code that I'm going to show you might look a little daunting for the first timers, but this is essentially here to make our lives a lot simpler. Let me explain how. So we are calling 4 different models: logistic regression from scikit-learn linear model, linear discriminant analysis from sklearn discriminant analysis, then we are calling decision tree classifier from scikit-learn trees, and random forest classifier from scikit-learn ensemble. And we are also calling the recall and precision score. Since we are going to be fitting the models, let's also discuss what should be the model performance measure for us. So for this kind of a scenario where 1 represents a machine failure, a false positive would be a scenario when there was no machine failure, but the model suggested there is a failure. And a false negative would be when there is a machine failure, but the model failed to identify. Now you can think for yourself, what has a higher impact? Of course, false negative is dangerous because it's a failure and you're not able to detect. On the other hand, false positive could be an unwanted check that you're performing, but that still is preventive. As they say, prevention is better than cure. So false negatives are more critical. Now, if false negatives are more critical for us, then which model performance measure we should be looking at? We should be looking at recall, because in the definition of recall, you have true positives divided by true positives plus false negatives. So we'll be focusing on recall as a primary model performance measure in this case. Next, what we are doing is we are instantiating all the models. In the first iteration, we will do this without tuning any model. As such, for logistic regression and discriminant analysis, we don't have too many choices to tune. For decision trees and random forests, we know tuning is a must, and we'll do that later, but we just want to see how does a baseline model perform. So we are creating these objects like logreg, LDA by the name of the models, DT base because this is a baseline model, RF base which is the baseline model without any hyperparameter tuning. Then we are creating a list called models where we have put all these models in this sequence because model training and predicting is a standard format. So since this is repetitive in nature, we'll do it by putting it through a loop, and we would like to see our output much more organized. You would often see codes where people navigate from one place to another, they scroll up and down to search their previous numbers, but this is going to give us a very neat output, and that's the reason we are putting it like this. Then we are creating 2 empty lists, essentially to capture the performance for recall on train and recall on test, and for now we can comment this piece for precision, because we are now clear that we are evaluating a model only on recall. What we're doing is we are running a loop over this list called models. We are saying for each model in models, if model is logistic regression or LDA, then we are fitting the X-train stats scale data. Remember, this is the data where we did outlier treatment, where we did multi-collinearity treatment, and we did scaling. So for stats-based models, satisfying their prerequisites, we are bringing the right treated data. Then we are doing a dot predict on the train data. We are generating the recall score using sklearn.metrics. We call this recall score. So we are predicting the recall score and appending it to this list so that it keeps on getting stored. Similar steps are being followed for test data. Of course, we are not going to fit on the test data, but we are going to predict on the test data and generate the recall score and append it to the recall score test list, which is here. So if the model was not logistic regression or linear discriminant analysis, then we go to the else condition. What does it mean? Now we're going to try the decision trees and random forest models. All these steps are identical. We are fitting, we are predicting, we are generating the recall score for train, and we are appending it to the list. Same steps for the test data. We are predicting, generating the recall score, and appending it to the list. Once we run this, this would have captured these two lists, which are going to be super useful. How? Let's see. So we'll write this one simple line of code, which is a data frame. We're giving a column called recall train, which will contain all the recall scores for train data for different models. Recall tests, which will contain all the recall scores for the test data for all these 4 models. And then we are giving index names as logistic regression, linear discriminant analysis, decision tree, and random forest. You can see how organized this output is. So in this case, if you see, the logistic regression model seems to be performing really bad because the recall is only 4%. Discriminant analysis, again, doesn't do that well. It's hardly 2.5 to 3% or 4%. Decision tree and random forest models are overfitting. The model performance on the training data in both the cases is 100%, but on the test data, they're not able to sustain it. Decision tree gives about 63%, and random forest gives about 62% model performance on recall. Now, of course, this was the baseline model. We should look at tuning the models. And how do we tune it? We can use grid search. So what we are doing is, for decision tree, we are choosing 3 hyperparameters: max depth, min sample leaf, and min sample split. Now, we've taken some values because this does take a lot of time to run, particularly for random forest, as we'll see later. But we're taking a shorter grid. We'll try to optimize the grid if needed be, but at least we'll give it a run first. So we've taken 3 values for max depth. We've taken 3 values for min sample leaf, and min sample leaf and min sample split. Generally, the recommendation is that split is taken 3 times that of the min sample leaf. So if we've taken 25, 50, and 75 here, we are taking 75, 150, and 225 here. These hyperparameters have already been explained in the video specific to decision trees, so you must have seen that. Now we are calling the grid search CV, where we pass the baseline model, which is the earlier model without any tuning. We are passing this parameter grid. We are doing a 5-fold cross-validation, and we are mentioning that the scoring metric is recall. Please note, this is very important. If we don't pass this, the model will be optimized on accuracy. And remember, our data was highly imbalanced, so accuracy should not be the measure that we should go after. Once this is done, to this grid, we are going to fit the train data, and then using the attribute called best estimator from this fitted model, we are going to get the best model. We are also printing the best hyperparameters. So let's just run this and see what are the values that we get. So it says max depth that we settle for is 7, min sample leaf we settle for is 25, and min sample split we settle for is 75. And at the same time, we've already stored a version of this model with the best hyperparameters as best TT, which you'll be using in some time. Now comes the time to run the random forest model, and this may take some time depending on your system's resources or how you're doing it on cloud. So you'll have to be a little patient. We've taken a relatively bigger grid here and 2 additional hyperparameters. So random forest is a collection of trees, we know that. So max depth, min sample leaf, and min sample split will stay the same, but we can choose the number of trees. So we've not taken like 200 or 100 trees. We are saying we'll create 10 trees, 25 trees, and 50 trees. And it also has an option to choose the number of features. So since we have only 6 features now, we have taken the feature count as 2, 3, 4, 5, 6, anything from this. Please note that the random forest and decision tree models are being fit on the copy of the data which we took earlier, which did not undergo the pre-processing that we did for the statistical models. So this data has more features. This data may even have outliers because decision trees and random forest models are not sensitive towards it. So we will run this. Again, the same thing. We have created a grid. We have done the cross-validation and scoring on recall. We are storing the best version of random forest using the best estimator attribute and also printing the hyperparameters. This will take some time. Again, as far as the grid is concerned, there's no right or wrong value for the grid. It's only optimized as we start running it. So for example, if we settle for a value, let's say for n estimators as 50 as the best value, then it is up to us to increase that value further and explore it. Likewise, let's say for max depth, we settle for a value which is 5, then we can try values neighboring 5 as well. For example, we can try 6 and we can also try 4 because it is trying to find out the best solution within the inputs that we have given. So grids can always be optimized. It's just that it can be a time-consuming exercise, but for real-world problem solving, it is definitely worth it. So can you guess how many combinations are being tried? We have given 3 choices for estimators. We have given 5 choices for max features. We have given 3 choices for max depth, 3 for min sample leaf, and 3 for min sample split. If we take a product of all these counts, those many random forest models are being tried. So 405 random forests are being created. And no wonder that's where it definitely takes time. Finally, the random forest model has finished running and it took almost 7 minutes. And if we look at the best hyperparameter combination that is found, it's found a max depth of 7, max features of 6, min sample leaf of 25, min sample split of 75, and n estimators as 25. Now you can imagine, we can of course try variations of these values. For example, for max depth, we only gave the maximum value as 7. So of course, if this was a real problem that you're solving, you should try to expand this grid further. So for max features, since we had only 6 features, we can't go beyond this. So we can't change this value further. It could have been a smaller value that we would have chosen. For min sample split, the minimum value was 75. Again, we can try smaller values, but that will take a lot of time. So we're not doing those changes, but you get the idea. For a real world problem, you try to visit this grid multiple times. In this process, we've already been able to store the best random forest model, which will have these hyperparameters already fitted to it. Now let's repeat the same code that I explained to you some time back. This is the same list of models that we created above. The only change is that we have brought in the best decision tree and best random forest now. Earlier, it was the base decision tree and base random forest model. We are again updating only the recall scores. So this precision is kind of redundant here. We don't need it. And we are fitting the appropriate model. If the model is logistic regression or linear discriminant analysis, then we are passing the data on which we've done a lot of pre-processing. If not, then we are just simply passing the train data as it was copied for trees. When we run this, this would store these two important lists for us. And we can, of course, look at the outcome as we printed earlier. Now you see the model performance for logistic regression and linear discriminant analysis has not changed much because we didn't do any changes here. But if you see decision trees and random forest model performance seems to have come closer in training and test set, but overall has come down. So if you see, the earlier performance for decision tree was in the range of 60s, and so was the case with the random forest. And now you can see this is 36 and 49 respectively. And even the train performance, which was 100% earlier, has come down. So they're coming closer, but they're still not achieving the kind of performance we'd be looking at. One of the reasons why this might be happening is because our data was highly imbalanced. The cases of machine failures were around 3%, and the cases where the machine did not fail were around 97%. So what we'd want to do is we would want to treat the data imbalance. Now there's a separate tutorial that we have created on multiple types of imbalance techniques, and I'm just taking one in this case, which is known as SMOTE or synthetic minority oversampling technique. This generates the synthetic observations using the logic of k nearest neighbors and generates the data where you will have sufficient records of ones compared to zeros. So we are calling this class from the library called Imbalance oversampling. If you're doing this on Jupyter, you may have to install this library first and then you can use it. But on Colab, this will work with just the same line of code that I'm showing you here. SMOTE is instantiated here because this is a process where the synthetic records are generated. It has a random state. We should mention that for reproducibility. Please note, SMOTE is only applied on the trained data. So you don't do it for the test data. So we are doing this fit_resample first on the variables that were subjected to the statistical models. And then we are doing it for the data which was subjected to the tree-based models. The output here will be the resampled X and Y sets for stats-based models and the resampled X and Y sets for the tree-based models. Both will be the training sets only. Let's run this. So now we have the same code which has a list of our models. We have taken the best versions of decision tree and random forest models already. We are not training them all over again to discover the hyperparameter space. But what we are doing is that to these models, we are now passing the data, which is the resample data. So for example, for the statistical models, we are taking the X data, which is X train resampled stats, Y train resampled stats data, which is what we got here. And then for the tree-based models, again, we are taking the resample data for X and Y, and that's what we are fitting. Please note here, for test, there would be no change. For the test data, we are still sticking to the data that we had parked earlier, separately for the stats models and the tree-based models. Let's run this code. It's already finished. Let's see what's the kind of output we get when we run this. Wow, so you see the jump in scores. Our logistic regression model was barely able to produce about a 3-4% kind of a recall, and discriminant analysis was even struggling with that much. But these models also have improved. The recall for train is 79.8 and for test is 77.4. Linear discriminant analysis, again, is in the same league, 80.6 and 77.4. So these models are definitely doing a lot better compared to where they were. But Let's look at the decision tree and random forest models, right? So decision tree is giving a 96% recall on training and a 92% recall on test. And random forest is giving a 96% recall on training and 91% recall on test. Obviously, when you compare the decision tree and random forest here, the decision tree seems to be doing better. Why? Because this is just one tree. Whereas in random forest, if we go back, the best hyperparameter for n estimators or the number of trees was 25. So if 25 trees are giving you a result, which is a notch below just a single tree, which a decision tree is, then obviously you'll choose decision tree as your best model. Now, since decision tree is the best model, as we are concluding, it gives the best performance on the test data as far as the recall is concerned. What we would want to see is what is helping this decision tree. What are the features that it considered to be the most important features? Because at times we also have to explain the models. How do we do that? We can call the attribute called feature importances on the best decision tree model. And then what we are doing is that we are sorting the features by the feature importances and populating a list of that, enumerating over the indices. Let's see what we get here. So you can see the feature importance is like this. So highest importance has been given to rotational speed, followed by the torque, followed by the tool wear time in minutes, then air temperature, and then process temperature. Finally, the type, the order column that we had is here. If we want to visualize this, we can also create a bar plot for this quickly. And here we go. That's one and the same information that we printed here. The rotational speed, the highest feature importance. This is required when we have to explain the features as well. So this was a case study where we tried multiple models and we saw a dramatic change in the kind of performance that we could get finally. We started with the models, especially the statistical models, highly underperforming, barely giving 4 or 5% kind of recall, which jumped to about 80% later. And we saw the random forest and decision tree models overfitting as they're typically supposed to be. We got somewhat better output in terms of controlling overfitting when we tuned those models. But the real game changer here was the data imbalance treatment, which we did at the last stage. I hope you had some meaningful takeaways from this case study overall, as this was a good comparison between the statistical models and tree-based models, and a lot of learning throughout the journey. Hope this helps. Thank you.